Let's be honest. We hear about AI all the time, but have you ever stopped to wonder how a machine, a hunk of metal and silicon, actually learns? Not just following a list of instructions, but genuinely getting smarter? Well, the answer is pretty amazing, and it has more to do with biology than you might think. And that's exactly what we're going to break down today. So let's start with the absolute core of the problem. A computer only speaks in ones and zeros, right? So how do you explain something like a cat? I mean, you can't just type in a dictionary definition. A cat has fur, sure, but so does a teddy bear. It has pointy ears. So does a fox. This one seemingly simple question was a massive roadblock for the smartest minds in computer science for decades. How do you bottle something so intuitive into cold, hard code? For a long, long time, the only answer people had was something called rule-based AI. The best way to think about it is like a giant hand-coded instruction manual. If it has whiskers, and it meows, and it has claws, then it's probably a cat. But you can see the problem, right? This whole approach is incredibly fragile. What if the cat is sleeping and not meowing? The whole system breaks. So we clearly needed a different way of thinking. What if, instead of feeding the computer the rules, we could get it to figure out the rules for itself? And hey, you don't have to take my word for it. AI researcher Gary Marcus puts it perfectly. That old if-then system just kept hitting a wall because, well, the real world is messy. It's complicated. There are always exceptions to the rules, always weird little problems that a programmer just can't predict ahead of time. It was a dead end. So if the giant instruction manual approach was a total failure, where did scientists look for the next big idea? Well, they turned to the single best learning machine in the known universe, the one sitting right between your ears, the human brain. The solution wasn't going to be found in more rigid logic. It was going to be inspired by biology. And this inspiration led directly to the creation of the artificial neural network, or ANN. So instead of one giant single program, an ANN is built from millions, sometimes billions, of tiny little interconnected units. We call them artificial neurons. Just like in our own brains, every single connection between these neurons has a certain strength, or a weight. These neurons are constantly pinging each other, kind of like they're voting on what the right answer is. And it's from this chaotic storm of pings and votes that patterns start to emerge. Oh, and when you stack a whole bunch of these networks on top of each other, that's what we call deep learning. Okay, so this is great. We've built ourselves a digital brain, this massive web of connections. But here's the thing. It starts out as a complete blank slate. It knows absolutely nothing. So the million-dollar question is, how do you actually teach it? How does this network go from knowing nothing at all to being able to look at a photo and say, hey, that's a cat? Well, that process has a name, and it is the engine behind pretty much every major AI system you've ever heard of, from ChatGPT to all the AI image generators. It's called backpropagation. And honestly, if you can get your head around this one idea, you'll understand the secret sauce of all modern AI. So how does it work? It sounds super technical, but the core idea is surprisingly simple. Let's just walk through it. Step 1, you show the network an input, like a picture of a cat. Step 2, the network, which at this point is just a bunch of random connections, makes a completely wild guess. It might say dog or car or banana. It has no idea. Step 3, you tell the network how wrong it was. You calculate the error in its guess. Now, step 4 is where the magic happens. A signal gets sent backwards through the entire network, telling every single tiny connection how to adjust its strength just a little bit to make a slightly better guess next time. It's like, hey, you, connection number 5,000, turn your signal down a tiny bit. You, number 12, turn yours up. And then step 5, you do it again and again and again, millions, sometimes billions of times. And this is a quote from Geoffrey Hinton, one of the absolute pioneers of this technique. He actually won a Turing Award for it, which is like the Nobel Prize for computing. And he describes it just like that. You're sending signals backward to tell the network how to change itself. The key thing here is you're not programming the knowledge in. You're just providing feedback and letting the network program itself. So when you really think about it, what's happening here is incredible. The AI isn't really learning what a cat is in the way we do. It's just learning how to make its guess progressively less wrong. The big idea is that AI learns not by being told the answers, but simply by being corrected. It's almost like a sculptor with a block of marble. Every wrong guess is one tiny chip away at the stone, and after a billion of those tiny corrections, an intelligent shape, the right answer, starts to appear. Now, this really unique way of learning, it has some pretty strange and, frankly, very human-like side effects. In fact, you could argue that the mistakes these systems make are just as interesting as when they get things right. I'm sure you've heard about this. Maybe you've even seen it happen. You ask an AI a question and it just confidently makes something up. We call them hallucinations. And most people see this as a huge flaw, right? A bug that proves the AI doesn't really know what it's talking about. But what if it isn't a bug at all? Well, here's Jeffrey Hinton again with a really mind-bending idea. He argues that when an AI hallucinates, it's actually behaving more like a human, not less. He compares it to this thing in psychology called confabulation, which is basically just a fancy word for our brains filling in the gaps in our memories with plausible details. Something we all do, all the time, without even knowing it. And this really forces us to change how we think about memory. We tend to imagine our brain stores memories like files on a computer, perfect, pristine, and ready to be pulled up. But that's not how it works at all. Our brains generate our memories on the fly, weaving together a plausible story from all these different connections. And that's exactly what an AI is doing when it hallucinates. Both are just creating the most likely story based on the patterns they've learned. So, if today's AI is already mirroring our brains in these strange and fascinating ways, where does this all go from here? What's the next step on the horizon for these thinking machines? Well, Hinton gives us a little glimpse into the future. He thinks the next big leap forward is going to come from making these AI networks even more brain-like. He talks about needing something he calls fast weights. Think of it like giving an AI a form of short-term memory. It's the ability to create new connections that adapt super quickly to new information, but then fade away just as fast, just like how we remember a phone number just long enough to dial it. Okay, so let's quickly recap the big ideas here. We started with those old, fragile if-then AI systems, which were a dead end. The huge breakthrough came when we decided to get inspired by the brain's structure. We learned that modern AI learns through a process called backpropagation, which is just a simple loop of guessing, checking for errors, and then making millions of tiny adjustments. And maybe, most surprisingly, this whole process leads to flaws, like hallucinations, that are actually incredibly human. And that leaves us with one last fascinating question to chew on. Right now, we see an AI's ability to hallucinate as a weakness, a bug that we need to fix to make it more reliable. But if that very flaw is also what makes it so strangely similar to us, what does it actually mean when the AI finally overcomes it and learns to be perfect?